to go with it. But I was trying to think of how to kind of demonstrate this. I'm going to shut all the lights off, and if I were to like turn my little light on like this, and so you guys need to look, and you're looking at my little light, okay, and pretend that you have a way of seeing how bright this is. You have to look at it. Now, what if I go out here, and you can see how bright it is? Is it brighter or dimmer?
Just a little bit.
Just a little bit. What if I go
You can move.
out here?
I can't see it.
Okay, we'll come to the door. Oh, it's dimmer. It's dimmer. So, you probably would have figured it would have been dimmer. But just that phenomenon of something's going to get dimmer the farther away it is, you're like, duh, right? So actually, we use that in astronomy to gauge distances. Because the deal is we know, if we know how much energy this is putting out and we know how dim it is, then we can use that relationship to get to the distance. So this is kind of about putting things in perspective with regard to distances. So the word astrology, of course, isn't astronomy. Astrology is your horoscope. Ology usually means like it's the study of something. But cosmology goes back to actually being the science of something, the study of something, the study of the cosmos is what cosmology is. And so that's kind of segueing into, last we met, we talked about how the galaxies were kind of arranged. That's the cosmology, okay? Study of kind of how the overall universe is set up. So in order to kind of place things in space like we did the other day, we talked about how galaxies are in clusters, and clusters of galaxies are in superclusters of galaxies, and they are arranged around these large void areas. We need to get a sense of distance. So this is going to kind of take you from closest distance on out. There's something called radar, and if you guys are like me, if you've recently looked at an image where you want to see the clouds, you're looking at a radar image where it's actually looking at a signal, and if the signal bounces back, you have some sort of precipitation. That's radar. Sonar is a type of radar. So that's relatively close. And actually, I don't know if you guys remember, but we said that you can't see through the clouds of Venus. And so what we did is we just put a spacecraft orbiting Venus and kind of let that spacecraft send down a signal through the clouds and look for that signal to come back to get the topography or kind of surface features of Venus. Parallax, this is a little bit farther down. We said you can actually use parallax, a star moving against background stars as the Earth orbits the sun, to get a sense for the distance to the star. Well, that bit that I did about with my phone, trying to kind of show you, it gets dimmer as it gets farther away, that whole thing actually is what we call using a standard candle. That would work assuming you kind of know how bright the phone is normally. So how bright it is normally is called its luminosity, how it's pumping out a certain amount of energy. Brightness is what it appears. So basically, we have how much energy is pumping out, how bright it appears, throw in a 4 pi, take the square root, and that will give you the distance. So those are using standard bulbs. And we're going to see actually in astronomy, we have certain different standard bulbs. The thing about a standard bulb is you need to know the luminosity, how much energy is pumping out. Okay. So this actually is none of them. This is an HR diagram. Hopefully you can kind of see the red and the blue. These are different groups of stars that were born. These are clusters of stars. There's the Pleiades clusters. These are the Seven Sisters. It looks like a little Dipper through binoculars. And then there's the Hyades. So they're the two different colors. And the HR diagram, we would call these the main sequence because you can kind of see the diagonal. But hopefully you kind of see that actually they are offset. And here's the deal. Actually, this line is drawn to kind of map or match up these two stars, are kind of similar parts on the HR diagram. But if I was to go over here and look to where the red one intersects, remember in an HR diagram, this is brightness. The red one is dimmer and the blue one is brighter. Okay? And that's apparent brightness. So that actually is a way to see that this whole set of stars called Pleiades, this cluster of stars, actually must be further from us, and the Hyades are closer. So we can kind of use that to our benefit to understand how far away that cluster of stars is by kind of matching up or understanding how the whole apparent brightness is shifted. Then there's this one. Actually, we talked the other day about how galaxies, the concept of a galaxy is relatively new. In the 1920s, they had this debate, the Curtis-Shapley debate, which actually is on your review sheet. And we didn't know if those kind of, those things that we now know as galaxies, if those were maybe just nebula. And so remember, kind of the last piece to fall into place was how far away are those objects. And amazingly, they could actually see a star in the Andromeda galaxy kind of changing its brightness, okay, on the HR diagram. It's kind of, stars will do that when they kind of leave the main sequence. So this is called a Cepheid variable star. So there's actually a little more to this Cepheid variable sort of thing. Each of these dots represents a Cepheid variable. And basically, the way it works is depending upon how quickly it kind of gets bright and dims, whether it's 3 days, 10 days, 30 days, 100 days, that actually can be directly related to how much energy it's pumping out. All right, so now we've got kind of a pulsating Cepheid variable star in a distant galaxy, and now we can actually see how long it takes to cycle one of its brightness cycles, and we can map up to what its real energy is that's pumping out. And like I've said before, we can compare what we know it's pumping out to how bright it really appears to get to its distance. So that's awesome. Now, each one of these has their own kind of limitations. And like this one says, you're kind of limited up to galaxies that are 100 million light years away, which seems like a way far distance. But remember, in astronomy, you have to be careful of your M's and your B's. Of course, million is smaller than billion. So this is actually showing you Cepheid variable star in the spiral arm of a galaxy. And if I was looking at, I don't know, I would probably say that looks like the same star, and the one that's kind of getting brighter or dimmer would be this one. Okay, now as I was getting ready for today's lecture, I'm like, drat, we didn't talk about that. And kind of to bring you up to speed, one of the things I tested you over for Unit 3 was this fact that we could have a pair of stars, a companion set of stars, and we could have this star is a nice swollen red giant, and this star over here is a white dwarf. And we talked about if they're close enough, the material from the swollen red giant can kind of dump on this white dwarf. And I said that actually it can get hot enough in the disk sort of region to create a thing called a nova, N-O-V-A. And a nova actually is just kind of an explosive event. It's like throwing off your blanket. And it's where actually hydrogen goes to form helium. Well, this kind of kicks it up a notch, and what I didn't talk about is we have another scenario, I'll put it over here, where again you have your swollen red giant, you have your retired white dwarf, and it's going to get dumped on, but it's going to actually get dumped on and dumped on and dumped on and dumped on, to the point that it's going to begin it's going to wake up in its core. So in its core, it's actually going to go ahead and, would that be right? Well, actually, in its core, it's going to begin fusion. And when this happens, there is an explosion, a big explosion, bigger than a nova. And this is actually called a supernova. And this is one of the many things in science I say, don't blame me. You're like, Mrs. Snides, you talk about supernova. That's when a massive star blows up. You're right. There's 2 types of supernovas. And don't blame me. actually call this one a supernova type 1A instead of supernova type 2. But my point is going to be that when this happens, when this explosion happens, we know its luminosity. And again, if you know the luminosity, the real brightness of any object like this, you can go ahead and compare how bright it appears to how bright you know it is, and you can get to distance, and that's exactly what we do. So this actually will reach farther than the Cepheid variables. So I just think that astronomers are such patient people. So this is showing you the galaxy. Galaxies, the farther away they get, kind of the more misshapen they look. This is a galaxy before the explosion. This is a galaxy far, far away after the explosion. Before, after, before, and after. I just think that's so cool, especially this one. You're like, really? We watched a video this semester that kind of showed a mechanical sort of telescope that all it did was to look at the heavens, to look for differences in the heavens. And it would pick up these subtle differences. That's amazing. So again, once we see this, that's a supernova, and we can understand that it's this specific type of supernova. We know its luminosity, so we compare how bright it appears to what we know it should, how much energy it's putting it out to get distance. So instead of an M, you're up to B's. So this actually will get to, this is pretty powerful. It will get to almost the edge of our observable universe. The edge of our observable universe is 13 billion, I want to say, or so, light years from where we are. So 10 billion light years away is pretty darn big. So this actually, if you read the caption, this actually is showing you a supernova type 1A event, just like this that I described. Problem with a supernova type 1A like this is it cannot, what we say, reoccur. It can't happen again because that white dwarf, dang, it came out of retirement and it died. This white dwarf comes out of retirement and actually can go back into retirement. All right. So here's finally where I have just a few videos to show you tonight. So this is Edwin Hubble, and he is at his telescope in Mount Wilson. It's a 100-inch reflecting telescope. So it uses mirrors, it's a reflecting telescope. 100 inches, that's humongous. So he actually is credited with, and I think the video is going to talk about it, looking at galaxies and seeing what we call a redshift in galaxies. Let's see if this will play for me. Play for me. Something's moving. This actually is trying to kind of show you the redshift. So what you're looking at is, this is kind of a normal, if something wasn't moving, if these galaxies weren't moving, this is what you would expect it to look like. This is the picture, though, of a galaxy that's moving away from us. So this peak actually corresponds, on the stationary one, corresponds to this peak on the moving one. So actually you can see where instead of about, 465 nanometers, it's actually here, it's a longer wavelength, about 490 nanometers. So the wavelength is longer. So bottom line, and actually that's one of the things we'll talk about with Unit 5 is that our universe is expanding. So this actually, or coming up on the next slide, is an image of kind of, or it's not an image, it's a graph that he prepared. So this sort of expansion is generally attributed to him. He discovered it, called Hubble flow. What you're looking at here is each of these little black dots now represents a galaxy. And like that gal in the video said, what they did was they plotted how far away the galaxy is from us in light years versus how fast it's moving. So she said if it's twice as far from us, it's moving twice as fast. So this recessional velocity is talking about that away movement. So if you know much about plotting, you can actually get some cool things, and your scatter plot looks like it has a straight line drawn through it. You can get some cool things from the slope of your straight line. And in this case, actually, the slope of the straight line is called Hubble's constant, and it can be used to kind of date back, not kind of, but date back to how old our universe is. This was Hubble's data. Again, the dots here represent galaxies, how far the galaxy is from us and how fast it's moving away from us. And then this actually represents a few years later, he added to that. So this cluster down here, was his data. Good job, Hubble. And then this data right here was a few years later. So it's kind of exciting when you find more data that continues to support the general slope of your original line. This, I think we've kind of looked at before, where this is looking then at not stars, but galaxies. So right in the center is us on Earth orbiting our sun, and our sun is a part of the Milky Way galaxy. And you can start to kind of see these different lights. These, again, lights represent galaxies, little colored dots. Now, the farther you get from us, you kind of see the red here, which is trying to imply the redshift in the light coming from those galaxies. Again, suggesting that redshift is because the galaxies are moving away from us. So here is an awesome telescope, and unlike what we do with our telescopes, we kind of put our eye to the eyepiece and kind of see what we can see. Actually, instead of that, we've got the image coming from the telescope is all kind of mapped here like this to really analyze the data. So to kind of summarize things, what we've talked about, that here's the Earth, and this is how far from the Earth we can gauge distances. So we said, well, the closest sort of gauging distances would be a radar, 10 to the negative third light years. And then we said, actually, you can use parallax. We talked about how you can find distances to stars using parallax, relatively nearby stars. Here's a figure to show you that. Then this one right here, we said actually we could have two clusters of stars, in this case the Pleiades and the Hyades, and we could see how bright they are, and this is called a main sequence fitting, and get a sense for how far away the Hyades were closer than the Pleiades. And then we move on to some kind of standard bulb sort of thing. So Cepheid variables, we know how bright it is, depending upon its period, so we can use them as a standard candle. We can use white dwarf supernova type 1A as the standard candles, getting even farther. And then actually we kind of have an overlap between using the type 1A supernovas as a standard candle and Hubble's law. Like I said, you can use its slope to actually get to, which is H0, to get to how old our universe is. Those are all ways of estimating distances. So, video.
Short one. See if this one will do any better. Pause. These are some of my favorite people. This is Minute Physics. Thank you, great job. Great work. Maybe.
And the reason we know that there's dark matter in the Milky Way has to do with the fact that and I think you're going to see a slide here with the Andromeda Galaxy, the fact that the stars orbit the center of our galaxy in a pattern that means that there's mass in the halo region, basically. The other thing we've talked about is how the galaxies are organized in clusters, and I said, and it's not just me saying it, but data says that those galaxies that are in the same family, in the same cluster, actually have a bit of gravity going on in between them. And actually that could be associated with the dark matter. Again, that's kind of in the halo region of all the other galaxies. So kind of like we did with the Milky Way, this is looking at how the stars orbit the center of the Andromeda Galaxy. So the red line is showing you how we see the star's orbit. It's got a supermassive black hole in the center of it too. It's a similar size as the Milky Way, the Andromeda Galaxy. The red is what we see, and the blue is what we expected based upon just kind of how gravity works. And so again, the difference between what we observe and what we expect means that it's not a curse necessarily. But this galaxy, like our galaxy, has dark matter in its halo region. So I'm going to go ahead and show you this video, I think, before I explain my slides. One of the things that we didn't do was to talk, what you see, here we are, we're the observer, and here's the galaxy, the thing, like she said, doing the lensing, creating a divot, dent in fabric of space-time, and here's the distant object that we actually get to see brighter because of this lensing. Okay, so anyway, so I just kind of finish off the subject showing you some gravitational lensing. This looks like that Einstein cross kind of. This kind of yellow object right here is a single object. The reason you see it 4 places has to do with kind of what she just said. We can see very distant things, just like we can use, we use one type of telescope uses lenses. That's that refracting telescope. So actually we're able to see more distant things using gravitational lensing. This is showing you, here is, we talked about how galaxies are in clusters. So there is a cluster of galaxies. And actually we just more recently talked about the fact that all those galaxies, picture them having dark matter in their halo region, and think of dark matter as kind of being strewn around this cluster of galaxies. We can get to actually what the mass of that dark matter is based upon how much gravitational lensing it does of distant objects. That's it. Yay, 5 minutes early, people. So tomorrow's optional. If you come, you get lab credit by watching a video. And like I said, still haven't figured out which video I'm going to watch. Probably, hopefully 20, 30 minutes, and then I'll have some questions to answer. You can answer on your own or answer in a group. If you don't come tomorrow, I guess I'll see you on Monday. If you don't come Monday, then I guess that'll be the test you drop. If you don't come Wednesday, then I guess I'll see you a week from Monday. That's the beauty of college, is you could just come or don't come, and it's wonderful.